Topic 7.2 deals with radioactive decay. And just to refresh ourselves for a moment, the nucleus is made up of protons and neutrons. They make up a large majority of the mass of the nucleus. And inside the nucleus, there are two primary forces at work. There's the electrostatic or Coulomb force that occurs between protons, so proton-proton interaction, and there's the strong nuclear force. And the electrostatic force, remember, is a repulsive force between like-charged particles. So these protons are pushing each other away. The strong nuclear force is acting like the glue that holds the nucleus together to overcome that repulsive electrostatic force. Now in nature, what we found is that there are many unstable isotopes of elements. And remember, an isotope is an atom of an element that has the same number of protons but a different number of neutrons. And so the chemical properties are similar, but the physical properties are different. And in some isotopes of some elements, we find that this process of radioactive decay occurs. And the process of radioactive decay is when the nucleus changes. And when it changes, it emits some type of radiation. And there are three types of natural radioactive decay: alpha, beta, and gamma decay, which are so named because of the types of radiation that they emit. And the difference between, or the distinction of natural radioactive decay, is that it doesn't need any type of external stimulus to occur. It just happens naturally. Now, why does this occur? It occurs because of the two main types of the two forces that we just mentioned that are occurring or interacting inside the nucleus: the Coulomb force and the strong nuclear force. The strong nuclear force is a short-range force. It acts over a very, very small distance. The Coulomb force is a long-range force. It acts over basically any range. The strong nuclear force, while at short distances, can very easily overcome the Coulomb force. Once you get past its maximum distance, it drops in strength very, very rapidly, and then the Coulomb force starts to become the dominant force. Now, if you look at the chart here, this is a chart of the number of protons versus the number of neutrons. And looking at this, we can notice a couple of interesting things. This dotted line here is the line that represents the number of neutrons equaling the number of protons. And you can see down here, and as we go up, and then within the graph, there are two other important aspects. This green section right here, stable nuclei. Those are nuclei that do not undergo natural radioactive decay. Then we have our unstable nuclei, which are shown in the red, right here and right here. Now, what happens as we get larger and larger nuclei, those protons start to get further and further away from each other. And remember, over those larger distances, the electrostatic force is still acting, and so those protons are still pushing each other away. But as they get further away, those neutrons, that strong nuclear force, can't act over the entire radius or the entire diameter of the nucleus. And so you can see we're having more and more, or relatively more and more, neutrons compared to protons. At the bottom of this, if you look down there at the smaller nuclei, you see that the number of neutrons and the number of protons are pretty close to being the same. But as we get up here, the larger elements, the number of neutrons vastly outweighs, or there's a lot more neutrons than protons. When we have about 75 protons, we're looking at about 110 neutrons. Okay? So the reason for that then is that you have to have more of that strong nuclear force. If there's not enough neutrons to overcome all of that Coulomb force, if there's not enough to act over that the relatively large distance of the diameter of the nucleus, then it's what we call unstable, and it starts to fall apart. So either there's too many neutrons or there's too many protons, and so as we know in nature, things try and be as stable as possible. Whether that's the lowest energy state for an electron, or whether that's the most stable state for a nucleus. And so in order to become more stable, the nucleus undergoes that natural radioactive decay. Now, a couple terms that we're going to need to know when we talk about the different types of decay. First is the parent nucleus. This is the thing that you start with. The parent nucleus is the unstable nucleus that's going to eventually decay. The thing that it ends up being is the daughter nucleus. So parent, daughter, straightforward progression. Transmutation is any time that we have an element turning into another element. Think of alchemy. Alchemists tried to turn lead into gold. That was transmutation. Didn't really happen though. Here we have natural transmutation, which is one element, an unstable isotope of an element, turning into another one through the process of natural radioactive decay. Strong nuclear force can't hold that nucleus together, so it decays. As we mentioned, it only works well over very short distances. So we start with our radioactive atom, and it radiates some particle, some energy, forms a daughter cell.